speaker is Herman Komper from the University of Stellenbosch, and he's going to talk.
Okay, cool. Thanks. Hello everyone. Can you guys at the back hear me? Okay, perfect. If I don't project, then just wave. Yeah, so I'm Herman. I lead a small group of researchers at Stellenbosch University. It's called the Language and Speech Lab. And I'm going to talk about a little bit the things we do and also give a little bit of a broader view on speech processing. Okay, I'll start in a weird way. There's this very cool book written in the late 1980s. It's a sci-fi book, and it's called The Player of Games. And the main character, I can't remember his name because I'm bad with the names, but he lives in this utopian world where basically all problems have been solved, and life is wonderful, no one needs to work, and people can just spend their time doing whatever they want, okay? And in this world, the society spends a lot of their time playing board games, okay? But this main character, he's extremely bored with life because he actually turned out to be a very good board game player, and he's mastered all the board games in this universe, okay? And he's extremely bored with life. And so the story goes on, and he goes to another planet where there are more difficult board games to play, and then he's happy with life again. Now, why the fudge am I telling you this weird thing? While I was reading this, I was thinking of speech and language processing. And so most of you have probably heard of this thing called ChatGPT. And if you are a person working in text processing, like textual language processing, you might be in a situation where you're asking whether all problems with text processing have maybe been solved now, okay? And which might make some people excited, but other people, like this main character, might be quite sad about that. Now, what you might not know if you don't work in speech processing is that large spoken language models have also come up in the last few years, and these models are also solving a lot of the tasks in speech processing. And speech can be quite different from textual processing, and a similar type of thing is happening to what is happening in ChatGPT land, in the text processing land, where it might seem that most of the speech processing board games have now been solved. And that's what this talk is about. I need to take a little bit of a step back and just tell you about speech. So conventionally, there's been two major tasks in speech processing. The one is speech recognition, where you want to build a system that takes in a waveform and outputs the words that's said in that waveform. Okay, so that's speech recognition. And how companies like Google would solve this traditionally would be to collect thousands and thousands of hours of speech audio and then have someone carefully transcribe that speech into words. Okay? And then you would build a supervised model that takes in speech and output the words on this thousands and thousands of hours of parallel data. Very intensive, difficult to collect. The other task in speech processing that people have worked on a lot is text-to-speech, and this is the opposite problem. So Stephen Hawking, when he spoke, that was a text-to-speech system where he would type out the characters, and that would then be converted into a waveform, and you would hear it. And in a similar way, in the old days, this was solved by collecting large amounts of parallel text with speech audio, maybe in a particular speaker's voice, and you would train a supervised model to go from characters to speech. But what's happened in the last few years is that we've started to build these large spoken language models. And these models can be trained without having access to the text transcriptions. They can be trained just on large amounts of unlabeled speech audio, and then you can actually use them downstream for things like speech recognition and text-to-speech. So here's a little illustration of the model called Hubert. Okay, so it's based on BERT, which is the text modeling approach. And very similarly to BERT, what you would do is you would mask out some of the inputs, those gray vectors, and then on the output side there at the top, you would try and predict in text land, you would try and predict the words for those masked out regions based on the other words in the sentence. Okay. Now, what Hubert does, it's a speech model. Speech is different from text. That will be a little theme in this talk. You don't have just words that you can mask out and then try and predict. So how Hubert works is it takes in speech and then it passes that through a feature encoder, and normally a convolutional neural network, that extracts something like acoustic features that captures something about the audio here at the bottom. And then what they would do is they would mask out some of those latent acoustic representations. And then on the output side, right at the top there, they would try and predict basically what's happening in those three grayed out vectors. And their targets on the output side, what they would do is they would actually use the original input, apply some clustering approach, which discovers something that looks like phones or sub-phonetic units, and you would try and predict those units from the masked out regions. Does that make sense? Just nod. Okay. And these models, you can train them without any text labels, just by by running massive amounts of speech audio through the model. And the cool thing that you can then do is you can actually train a model like this on maybe 1,000 hours of unlabeled speech, and then you can fine-tune it for a task like speech recognition using a very small amount of data. There's several models that kind of follows this spoken language modeling approach. So I note a few there: contrastive predictive coding, WAV2VEC2, Hubert, WAV-LM. And what these models enable is that you can build a speech recognition system on as little as 10 minutes of audio. In the WAV2VEC2 paper, you can go and read that. They show that you can build a whole speech recognition model with much, much less data. Okay, so these big models that you can train without access to any labels are really solving many of the tasks that we as speech researchers have been working on. And so I started asking myself, is speech processing solved? Is this now done and I should find something else to do with my life? And through discussions, like I spoke to some of my students, I'm like, oh, is this solved? And they were like, oh, it might be, but I'm really struggling with this and this and this and this, okay? And through discussions with the students and thinking a little bit, I think there's a number of areas which are still untackled and unexplored territory, and areas that spoken language models can actually help us tackle. And I'm going to briefly mention 3 of these areas in this talk. The next 2 talks that follow, when Matthew and Leanne will speak, they will also talk about specific cases where these language models aren't just directly solving the task, and we need to think about things quite carefully. So I think the one cool thing that these spoken language models are enabling us to do is actually to go back to some of the speech science questions to understand the fundamental signal of speech better. Okay? So this is different from engineering, where we want to solve tasks. Here we want to use computational models to understand the underlying process of speech a little bit better. Now, to make this point, I want to just emphasize again that speech is different from text. If I write down the word humor and I want to generate the spoken utterance corresponding to that word, the characters itself isn't enough to tell me how to generate that spoken utterance. On their own, they aren't enough. So what you can do is you can take the character's humor and you can convert that to the phonetic units that's that corresponds to that word. Okay, so there I've written out the phonetic units in one of the phonetic alphabets. Okay, that is still not enough for me to know how to actually generate the corresponding audio. I also need to know something about the rhythm. How long is a particular speaker going to take for each of the phonetic units? Or maybe in a specific language, some units are longer and some units are shorter. I also need to know stuff about the intonation. So I can say humor, but I can also say humor. Okay, 2 different intonations. And within one word, I changed it into a question, which is pretty amazing. I need to know about the stress. How loud are parts of the speech? And then finally, there's a whole bunch of stuff that I haven't even mentioned yet, which are particular to a particular speaker. If I'm a male speaker, I will speak with a lower pitch. There's a bunch of things corresponding to timbre, like maybe I have a very husky voice, and I need to encode that as well. And many of these things, then you basically need to figure out all these generative factors in order to generate a spoken utterance. Does that make sense? And in speech science, many of these things aren't actually completely understood yet, okay? And as a concrete example, there are still arguments about whether phonetic units actually exist, or to what degree they exist, or how they interact. And we can start to use spoken large language models to answer some of these questions. As a concrete example of this, one of my students have looked specifically at rhythm modeling, okay? And what Benji van Niekerk, was he started by taking Hubert, and he looked at the discrete units that Hubert discovers, and then he started clustering them, okay? He just takes the units and he does this hierarchical clustering. And the cool thing that he discovered was that some parts of the hierarchy actually corresponds not to specific units, but to broader classes of phonetic units, okay? And so, for instance, the clusters highlighted in red here corresponds to fricatives. Okay, now these are units like s and z, where you basically like obstruct your vocal tract in a way and let air out. And he found out, these units actually correspond to these sounds. Now, that wasn't encoded. There wasn't text involved anywhere. And it just emerged in the way that the model was trained. How does he know that those units correspond to fricatives? You basically listen to it, okay, in a way. And one way to listen to it, which I will quickly play you, is what he can do is he can take original spoken utterance, he can extract the units for that utterance, and then he can stretch out everything that's in the red zone there. He makes them longer, okay, which means they will be more pronounced. So I'll quickly play you an input utterance, and then I will play you a modified utterance where the fricative, well, not the fricatives, where those classes, the red units, have been stretched. And then, so listen out for this and z sounds. Let's see if this playing works.
Carbon dioxide and water contain no potential energy, since the affinities of their constituent elements are completely satisfied. Carbon dioxide.
Okay, so that's the input to the model. We haven't modified it. Now we're going to just stretch out the red bits.
Carbon dioxide and water contain no potential energy, since the affinities of their constituent elements are completely satisfied.
Can you hear? So all the S's and the Z's got longer. He took some other clusters, so these clusters correspond to something like vowels.
Carbon dioxide and water contain no potential energy, since the affinities of their constituent elements are completely satisfied.
Okay. There are other categories as well. Stops. So these are hard to pick up at listen out. Stops sounds like b, p, t, where you have a little bit of a silence before you go into the sound. So listen at the end of water and possibilities, I think.
Carbon dioxide and water contain no potential energy, since the...
Okay, so she really, that really came out. I'll skip the last one. So that's just some examples of how you can actually uncover what these models are learning on the inside. He used this in a system specifically for rhythm conversion. And rhythm is interesting because it's unique to specific languages, but it can also be specific to specific speakers. So he used this in a voice conversion system. So this is a system that takes one speaker's voice and tries to convert it to another speaker. So you want the same content in a different voice. And you want to convert it based on a very small sample of your target speaker. Does that make sense? Okay. And in this case, what he did was he took one speaker that speaks relatively slow, and he tries to convert it to a speaker that speaks quite fast. Okay. And neither of these speakers are actually seen during training time. And that's also important to emphasize. So I'll just play the input here.
She can scoop these things into three red bags, and we will go meet her Wednesday at the train station.
Okay, and then the output. Remember, this model has never seen any of these speakers.
She can scoop these things into three red bags, and we will go meet her Wednesday at the train station.
Okay, so that's like artificial voices, and it's all generated by just modifying these units to match rhythm. So that was just one example, I think, of where spoken language models are being useful in order to answer speech science questions. The next area that I want to talk about is cognitive modeling, specifically cognitive models of language acquisition. So again, this is kind of the holy grail of linguistics. How does a small human infant acquire this ability to learn language, right? And a child gets exposed to many things when they're popped into the world. They get exposed to unlabeled speech audio in their surroundings. They get exposed to visual signals that co-occur with the speech signals. So if the parents of this child probably tortured them, but while they were like taking the photos, they said, here's a snitch, and the child is playing Quidditch. So while the audio is coming in, there's also a visual signal coming in, and the child might be able to use that as a grounding signal for learning things. And then as a child grows older, before they can properly understand language, they can already start to interact with the environment. And you might want to understand these processes better, like how the fudge does this amazing thing happen without the child ever seeing any text, right? There's no text in a 4-year-old, although the child has a pretty good speech recognition system. And we might want to model finer-grained things in order to understand things like learning difficulties early in life. If we have a very good cognitive model of how people learn language, of how humans learn language, then you can use that model to uncover maybe issues and problems that a child might face. I can state that a little bit more in engineering terms. So imagine you have a robot, okay, so not children anymore. You have a robot that you plonk in a room. That robot just gets exposed to a bunch of unlabeled speech audio. It doesn't know the language. It doesn't know, the words that's used in the language or the phonetic units. And the goal of the system should then be to say, okay, well, I want to learn where words start and end in the speech stream. That's an example of word segmentation. And then once I've learned these little chunks that correspond to words, I want to group them together into these things that you could call lexical categories. And then maybe I want to uncover the subword units, the phonetic units that's learned in this language. And if we can build a model that can do this, then we could maybe understand human language acquisition a little bit better. So one example of this wasn't done in my group. It's a group in Paris that did this, where they basically used contrastive predictive coding as a language learner. And what they did was the solid lines there at the top. Just look at the top graphs. What they do is they expose the model to English, and then they test it on French, and basically see whether an English model, as you give it more and more data, whether it gets better at English. But then at the same time, it also tests whether an English model, so an English child, whether it gets better or worse on French. Okay, and without going into the full details here, just look at the two top graphs. The one on this side is phonetic discriminability, basically whether the model can distinguish between phonetic contrasts in English. The dark black line is an English model, and the dashed line is a model that's being tested on French. Okay. And what you can see is as the model is trained on more data, it gets better. It's trained on English data. But at some point, the French starts to plateau out, that dashed line. Actually, on this graph there at the top, that's testing word discriminability. And what you see is, as the model gets exposed to more and more English, it gets better on words in English. That's the dark black line. But it actually never gets really good in discriminating between words in French. That's the dashed line. Now, this group in France, they're doing a ton of stuff, testing things like, do we speak differently to children than to adults, and how does that affect downstream performance? So that's just one example of how we can use these things to answer fundamental questions about speech. This is an example from one of my papers where we built a new unsupervised word segmentation algorithm. So this is an algorithm that's exposed to a lot of speech data. It's not labeled. And then the model is trying to figure out where words start and end. You might think that that's actually an easy task if you haven't done a lot of signal processing. When I speak, there's actually no spaces between words. You can't pick them up in the signal. You can actually, on this green spectrogram, it's actually quite difficult to see where words start and end. The word I starts there in the middle of that green spot. It's very, very difficult to see where words start and end. But we develop an unsupervised model to try and basically segment words out of speech. I'm not going. I can maybe quickly play you some examples. So afterwards, you can ask. So you bombard this model with a bunch of English data, and then you ask it, okay, you've learned a word. Play word 1214. What is that word? What do you think is the most common word in English? The Okay. Same model applied to Tsonga. So it's part of a word fanele that this model learned. Okay, cool. So those tasks that I just mentioned, they come from the scientific end, and we want to understand the underlying process better. There's still actually very difficult engineering tasks that we can also basically solve with large spoken language models, but these problems are still not unsolved. And I just want to mention a few of these. So one problem, sorry for the very awkward photo there. One problem is, imagine I've got my lecture video introducing machine learning concepts, and I want to take that video and I want to generate the same video, but I want it to be in isiZulu, but with my voice. Okay. One thing that you can do, and this actually works, is you take my video, you pass it through a speech recognition system, you get out text in English, you take the text in English, you push that through a machine translation system, you get out text in isiZulu, okay? You take the isiZulu text, you pass that through a text-to-speech system, and you get isiZulu speech out. That can actually work, and people actually do this. The problem with this approach is that isiZulu sentence coming out there, it sounds nothing like me, okay? Because the moment I go from speech to text, I've removed all my prosody, the intonation, the expressiveness in the speech signal got removed. And now you have to stick it back in here in some way on the output side. How the fudge do you do that? So generating expressive speech, I try to be like quite boomy in my lectures, right? And sometimes a little bit sad when things don't go out the right way. How do you actually capture that if you've removed all of that content from the signal? In game development, this often happens. So if you're a game developer like Ubisoft, you want to, sometimes a character wants to be very like loud and sometimes softer. How do you actually generate voices in that way? Ubisoft also struggles with this problem of generating paralinguistic sounds. So these are things like laughs, grunts, and cries, which it sounds so stupid, but you know, what is a laugh? Okay, so if laugh is labeled in a speech corpus, there are so many different ways to laugh in different contexts. And how you actually generate those things, you can't just follow the standard speech recognition or text-to-speech approach to tackle some of these problems. We started a bit late, so I feel a little bit done in, but I will try and finish on time. I've basically tried to convince you that there are still many interesting speech problems to solve. And I think the most interesting problems are those where we can't just apply speech recognition directly. Some of these problems is in the science domain, basically trying to understand the underlying principles of spoken language better. But there are still many open engineering challenges as well. I think this fourth point, which I didn't really touch on, speech recognition to some extent is solved, but on another degree, it's also not solved. So I think we should really think about specific areas, partnering with specific problem domains when we're tackling speech recognition problems, not just saying, like I've done in the past, I do low resource speech recognition, very generic, but actually focusing on real engineering problems that we can solve.